In this video, we're going to do a brief overview of what is a series. Now, a series is simply going to be the sum of a sequence. To give you an idea of what this will look like, here is an example of a sequence. Example of the sequence is going to be 1 over 2 raised to the n power. If we were to start at n equals 1, we would get 1/2, 1/4, 1/8, 1/16, and so forth and so on, corresponding to n equals 1, n equals 2, n equals 3, n equals 4, and so forth and so on. A series will make use of the summation notation that is hopefully familiar from back in Calc 1. So the summation from n equals 1 to infinity of 1 over 2 to the n. This would be the same list of numbers, but instead of simply a list, we would be asking for the sum of all of these. So really, when we say a series, essentially what we're saying is the sum of an infinite number of terms. Now, how can it be that the sum of an infinite number of terms wouldn't just be infinity? Well, it depends on how quickly your sequence is going to 0. So more generally, if you have a sequence, the notation that we tend to use for that is like this. A couple things that are left out, though implied, would be the starting point and the ending point of the sequence. So again, this would simply be a list of a bunch of numbers. A series will use the same sequence, a sub n, indicate the starting point and the ending point for the series below and above the capital sigma. This indicates to actually add together all of these terms. For a sequence, we define terms of convergent and divergent to correspond to whether or not, as we tended toward infinity, the sequence would actually arrive at a value. We're going to do something similar for a series. The way that we do so is by defining a partial sum. A partial sum of a series is the sum of a finite number of terms. Of the series. What we tend to use for partial sums is if we were given this series, the corresponding partial sums would be capital S. S1, for example, is asking you to add only the first term. The second partial sum is asking for the sum of the first 2 terms. The third partial sum is asking for the sum of the first 3 terms. The fourth partial sum is asking for the sum of the first 4 terms. However, it should be pointed out there is a recurrence relation for each of these. This technically would be the first partial sum plus the next term. This would be the second partial sum plus the third term. And this would be the third partial sum plus the fourth term. If we were to skip forward a bit, we could define the nth partial sum as being the n-1th partial sum plus the nth term. For example, heading back up to the series that we had at the top of the page, the first partial sum would be 1/2. The second partial sum would be 1/2 plus 1/4, which is 3/4. The third partial sum would be 1/2 plus 1/4 plus 1/8. Getting a common denominator, that would add up to 7/8. And the fourth partial sum would be 1/2 plus 1/4 plus 1/8 plus 1/16. That'd be 15/16. Now, big part of success when it comes to series is the ability to notice patterns. The pattern that I happen to notice is that the denominator each time is going up by a power of 2. So your denominator is simply going to be 2 raised to the nth power. And in every single one of these cases, the numerator is simply 1 smaller than the corresponding denominator. 1/2, 3/4, 7/8, and 15/16. One might speculate that this is what the nth partial sum would look like. To evaluate the sum of a series is simply to take the limit of the sequence that is the partial sums. So convergence or divergence of a series would be to consider the sequence of partial sums. If this sequence converges, then the series converges. Otherwise, the series diverges. Let's suppose for a moment that my speculation on the previous series was correct. In the event that my speculation was correct, we could evaluate the sum of this series by considering the limit as n goes to infinity of the partial sums. That is, this sequence of partial sums. So we would be considering the limit as n goes to infinity of 2 to the n minus 1 divided by 2 to the n. There are a number of ways to evaluate this. L'Hopital's rule is one. I'm actually going to use an algebraic method for this. This will be the limit as n goes to infinity of, I'm going to distribute the 2 to the n to each of these terms. So 2 to the n divided by 2 to the n minus 1/2 to the n. Now the first term reduces to 1, and the second term is going to converge to 0, which means that this is going to converge to 1. Therefore, the series converges to 1. Now, something to make note of regarding this series is that the corresponding sequence of values converges to 0. This is quite important. In fact, if the corresponding sequence either fails to converge or converges to any other value, it is guaranteed that the series will not converge. This has a special name, and it is called the Divergence Test. The Divergence Test states that if a sequence diverges or converges to a non-zero value, then the series, the sum from n equals 1 to infinity of that sequence, is guaranteed to diverge. To give a slightly more in-depth explanation of this, in section 11.1, I referenced the following sequence a couple times. And the sequence was n over n plus 1. Now this was a sequence that converged to 1. So we'll note that if we take the limit as n goes to infinity of n over n plus 1, that'll be equal to 1. So essentially what's going on is the sequence starts with finite values of 1/2, 2/3, 3/4, 4/5, 5/6, etc. And those correspond to n equals 1, 2, 3, 4, 5, so forth and so on. What happens is that as n gets large, essentially what goes on with your sequence is basically 1, basically 1, basically 1, basically 1, and so forth and so on. Now the reason that that's an issue for a series is due to the following. We're adding all of these terms. So once n starts getting sufficiently large, the terms of the sequence are, for all intents and purposes, 1. Which means that I will essentially be adding 1 to itself an infinite number of times. If I add 1 to itself an infinite number of times, then this diverges toward infinity. Therefore, the series diverges.